Have you ever found yourself in a situation that defies logic? Imagine this scene. You have two apiaries. They are separated by an air distance of only 500 meters. The same genetic line of queens, the same age of comb, the same feeding, the same beekeeper managing them. But the results are completely opposite. At the first apiary, the one on the sunny slope, in June you have 10 full frames of brood. The traffic at the entrance looks like a highway at peak season. The hives are heavy, the bees are calm, and the honey supers are full. Just 500 meters away, in a small depression near a stream, the picture is different. The colonies barely maintain 6 frames of brood. Development is delayed. By July, while the first apiary is booming, this second one is entering a quiet decline. The bees are nervous, and the yield is cut in half. A beginner beekeeper will say, "That's luck." A more experienced beekeeper will suspect, "It's genetics. This line of queens isn't good." Both are wrong. The difference is not luck. The difference is not genetics. The difference is in what you do not see, but the bee feels with every receptor in its body. The difference is in the energy equation of the location. So far in this series, we have analyzed physical factors, water and soil. Today we go one step further. Today we go to the core of the problem. We will not talk about honey yield as a gift of nature. Today we will talk about the price the bee pays to bring that honey. Welcome to the 6th episode of the series on choosing a location. Today we learn the mathematics of survival. Definition: the hive as a thermo engine. To understand why one location wins and another loses, we must stop looking at a bee colony as a box full of insects. We must start observing it as it truly functions as a biological thermodynamic engine. The foundation of everything, the absolute foundation of beekeeping, is not the number of bees. The foundation is the energy balance. What does that mean in practice? A bee colony has one biological imperative that it never abandons under any circumstances: maintaining homeostasis. In the center of the brood nest, where the new generation is born, the temperature must remain constant, 34.5 to 35 degrees Celsius. This is not a recommendation, it is a law. If the temperature drops, larval development slows down or stops. If the temperature rises, the brood is literally cooked and dies. In addition to temperature, the colony must maintain specific humidity so the eggs can hatch, and it must provide a constant supply of food for thousands of hungry larvae. All of this costs something. In beekeeping, the currency is not money. The currency is energy, and energy is honey. Your location determines the exchange rate of that currency. On a good location, the bee spends little energy to maintain those 34.5 degrees. The remaining energy, all that surplus, becomes honey in your jars. On a bad location, the bee spends all its resources just to survive, to heat a cold habitat or cool an overheated one. For you, the beekeeper, nothing remains. Let's do the math that most beekeepers ignore. First factor, the cost of flight, fuel. How much does flying cost? Scientific measurements are clear. A worker bee during one flight, depending on load and conditions, consumes approximately 8 to 10 milligrams of fuel, honey, just to power its flight muscles. It may sound small, 10 milligrams, invisible to the naked eye. But let's apply the law of large numbers that governs a strong colony. Take an average strong colony at peak season. You have an army of 15,000 active foragers. Each of them, under good conditions, makes 8 trips per day. Take a calculator. 15,000 bees times 8 flights equals 120,000 individual flights in one day. If the average fuel consumption is 9 milligrams per flight, 120,000 flights times 0.009 grams equals 1,080 grams. More than 1 kilogram. Listen carefully. Your bees can consume over 1 kilogram of honey per day just for flight fuel before depositing a single gram of surplus into the honey super. That is a fixed operating cost. That is the tax on flying. And now we introduce your location into that equation. What happens when the location is not ideal? That tax increases drastically. Second factor, aerodynamic resistance, wind. The first enemy of energy efficiency is wind. If you placed your apiary in an exposed, windy area where the hive faces constant airflow of 15 to 20 kilometers per hour, you have drastically increased your bee's cost of living. Why? Because a bee is not aerodynamically perfect. Wind throws it off balance, pushes it off course. To maintain direction, it must use corrective muscles. It must fly under full throttle. Landing on the entrance in strong wind is like landing an airplane in a storm. Enormous energy is spent on maneuvering. In addition, wind physically pulls heat out of the hive through walls and cracks, forcing the bees inside to consume even more honey to heat the brood. Practical experience and measurements show a brutal truth. Exposed apiaries have 10 to 20% higher internal honey consumption during cold spring periods. Let's translate that into lost money. If an average colony during intense spring development consumes 20 kilograms of honey for its own needs from March to black locust bloom, a 10% loss due to wind means 2 kilograms of wasted honey per hive. You have 50 hives? 50 hives times 2 kilograms equals 100 kilograms of honey. Your poor decision not to protect the apiary from wind has eaten 100 kilograms of honey before the black locust even bloomed. That is 100 kilograms you did not extract, or 100 kilograms of sugar you had to buy to keep them alive. The location charged you a penalty, and you did not notice. Third factor, thermal depression, cold basins. The next yield killer is the phenomenon we discussed earlier, temperature inversion. Many beekeepers like valleys. They are sheltered, they seem calm, but valleys are traps for cold air. During the night, cold air, which is heavier, flows down and settles at the bottom. A difference of just 2 degrees Celsius in average night temperature between a valley and a slope can be fatal for early spring development. Why do those 2 degrees matter? Because bees heat the brood. If it is colder outside, bees must cluster more tightly to conserve heat. A tighter cluster covers a smaller area of comb. A smaller comb area means less space where the queen can lay eggs. A cold location can reduce brood area by 1 to 2 frames at a critical moment of development. Let's calculate again. This is the math of missed opportunity. One full Dodont Blatt brood frame contains about 3,000 to 3,500 future bees. Losing 2 frames of brood due to cold means 6,000 to 7,000 fewer bees in your army. Those bees were supposed to be foragers during the main nectar flow. If one bee during its lifetime brings an average of 1/12 of a teaspoon of honey, about 5 grams, the loss of 6,000 bees is a simple and painful calculation. 6,000 bees times 5 grams equals 30 kilograms. You heard correctly. One colony on a cold location, delayed by just 2 brood frames, can theoretically produce 30 kilograms less honey than the same colony on a warm location. Multiply that by the number of hives. The losses become astronomical. Fourth factor, humidity and phenology, systemic error. It does not end there. Cold basins often retain moisture. Excess humidity in the hive is a silent energy killer. Nectar that bees bring in contains up to 80% water. To become honey, that water must evaporate below 18 to 20%. If your apiary is in a humid depression, the air is already saturated. Bees cannot dry honey passively. They must actively ventilate. They must station hundreds of bees at the entrance, fanning their wings to push moist air out. Every bee standing at the entrance ventilating is a bee not collecting nectar. That is lost labor force. If 300 bees must ventilate instead of forage, that is a daily loss of 1.5 kilograms of potential intake per generation of bees. A location in a humid depression does not kill the colony immediately. It slowly drains it, systematically, quietly. And finally, phenology, timing. Altitude plays a crucial role. A difference of 100 meters in elevation can shift black locust bloom by 5 to 7 days. If your apiary is at a lower, warmer elevation, your colony exits winter earlier and starts brood earlier. When the flow begins, it is ready. The apiary at a higher, colder elevation is delayed. The flow starts, and the colony is still developing. A meadow without an army. Remember that term from the previous episode? If you miss 5 days of peak flow because your colony is not ready, average intake on black locust can be 3 to 5 kilograms per day. 5 days times 4 kilograms equals 20 kilograms of pure loss. Cumulative effect and beekeeping practice. When we add all these factors together, the picture becomes alarming. Loss due to wind, 2 kilograms. Loss due to fewer bees from cold, 30 kilograms potential. Loss due to ventilation, 1.5 kilograms. Loss due to timing, 20 kilograms. When everything is added up, the difference between a perfect and a poor location can be 40 to 50 kilograms of honey per hive in one season. Same queen, same equipment, only a different energy equation of the terrain. What does this mean for you? What is the practical application of this theory? Field experience confirms this math. Apiaries placed on gentle southeast slopes where morning sun wakes bees earlier, with natural wind protection, forest or hedgerow behind them, above fog and frost zones, with a stable water source nearby. Such apiaries in spring have on average 1 to 2 brood frames more than competitors in the valley. They have 15 to 30% more foragers when the first bloom opens. That is not coincidence. That is physics. As a beekeeper, you cannot influence the market price of honey. You cannot influence whether it will rain during black locust bloom. But you can and must influence the energy balance of your hives by choosing the right location. Today we proved that colony strength is not a mystery. It is the result of subtraction. Colony strength equals energy collected minus energy spent on stress. Your task is to minimize that minus. Every meter the bee flies less to water, every degree of heat preserved from wind, every gram of honey not spent on ventilation, that is your profit. That is the difference between hobby and professionalism. If this analysis opened your eyes to how invisible factors steal your honey, support this series. Like the video because it helps the algorithm show this math to other beekeepers. In the comments below, write, have you noticed differences in colony development at different locations in the same year? Your experience is valuable data that confirms or challenges this theory. Write to us. So far, we talked about theory, factors, mathematics. But how do you know if your location is good before you bring the bees? How do you measure what cannot be seen? In the next episode, we move from words to action. We will analyze concrete tools and methods, how to measure microclimatic parameters of an apiary, and how to move your location assessment from feeling to precise data. Thank you for your attention. Protect your bees and choose wisely. See you in the next episode.